just have a look. The last presentation is from Georgia Tech, the YeSeul Kim. And this is actually a video presentation. So maybe I have to play this video on YouTube for everyone. So maybe now let me share my screen. Just 1 second. Okay, so can everyone see my screen? Can anybody just give me a short feedback? So
yes.
Okay, thank you very much. And I'm going to play this video for YeSeul Kim, but I believe maybe she will be also available for some Q&A afterwards. So now let me play the video.
Good afternoon, everyone. This is YeSeul Kim, and I'm a PhD student at Georgia Tech. And today I will talk about our recent work on development of a highway long condition monitoring framework using UAV images. So to give you a brief overview, monitoring and maintenance of a highway asset is very critical for civil infrastructure management, especially lawn mowing control near highway is very important in terms of safety because tall grass can obscure drivers' vision to detect traffic control devices and may lead to accidents. So this low maintenance work is usually done by third-party contractor, and their work will be inspected by local DOT personnel if the mowing is well extruded to the certain height or if there is any bare spot to be repaired. However, this type of manual inspections and manual measurement of grass height can take significant amount of time, and sometimes the people have to go to dangerous regions to measure the grass height. So there has been a need to automate this process. And in the meantime, there has been great advancement in deep learning and computer vision algorithms, and several researchers aims to leverage these technologies for civil infrastructure monitoring applications. So in this project, we also aim to leverage these UAV technologies to automatically detect grass areas and classify them into 3 categories, which are interest of the low maintenance personnel. So we define 3 categories, which are mowed conditions and unmowed conditions and bare spot as shown in the pictures. But there is some challenges with this method. So the major problem is that there is high variability of grass images because grass itself tends to vary a lot over different seasons, and images taken at different heights or angles will have different resolutions. So these will undermine the image classification models. And we also need to present our classification results in more user-friendly manners in order for our users to fully utilize our method. So the goal of this project is to develop a computer vision-based loan condition monitoring framework, which is integrated with user interface so that it visualizes the outcome in a very user-friendly manners. So here is our research overview. We have data collection, data processing, and development of models, and we'll discuss everything in more details. So for data collection, we aim to collect a large volume of data set using drone platform. So we used DJI Mavic Pro, which is equipped with 4K cameras and GPS sensors. And we set up the flying path over the target areas using mobile app, which is shown in the pictures. And we used various combination of flying parameters. And we also went to the data collection over 12-month period so that we can capture the wide range of grass conditions. After data collections, we conducted pixel-wise image labeling into 4 different categories, which were mold, unmold, bare spot, plus miscellaneous, which is everything other than grass areas, including roads, trees, etc. And in order to reduce the amount of manual labeling work, we used 2D, 3D co-labeling method, which was proposed in our previous work. So simply, we created 3 point cloud data using area images with structure from motions algorithms. And once we labeled these 3D models, we were able to project 3D annotations onto the 2D image pixels. And then we also applied patch augmentation strategies, which was to process N by N grid over the original images as well as the ground truth images. And those were divided into smaller pieces, and we used those smaller pieces as our inputs. This was to make our classification model more robust to the variability of images. Then we developed pixel-wise grass condition classification models using UNet architecture, which is one of the most widely used CNN architecture for semantic image segmentation. So UNet has 2 components. The first component, which is encoder, is consisted of alternating convolution and pooling operations, which allows models to increase the number of feature maps by downsampling the feature map. And this will pass on to the other component, which is decoder. So it will upsample the feature maps. So with this contracting and expansive operations, UNet architecture can propagate the feature informations to later layers with higher resolutions. So it can capture very detailed segmentation informations. So here is our result. The overall accuracy was over 90%, indicating that our model was able to produce acceptable performance compared to other benchmark models. And for each class, unmode class has the highest accuracy, followed by mode, miscellaneous, and bare spot. We believe that the low performance in the bare spot is attributed to the data imbalance because there was very small number of data for bare spot in our data set. And as for different data sets, our model tends to show lower performances for certain data sets if the locations have very significant physical changes as shown in the pictures. So here is some of the examples of our results. So as you can see, our model can distinguish mode and unmode conditions fairly well, but there is this small areas of bare spot which it was not able to detect. And lastly, we implemented our results on the GIS platform. So in order to produce this outcome, we generated an orthophoto by stitching whole drone image sets, and we placed the outcomes on this GIS platform for users. So for conclusions, we saw that our proposed framework was able to successfully detect grass areas from other highway assets, and we're able to classify these grass conditions using varied sizes of area images and proposed UNet architecture. But at the end, we saw that there is a lower accuracy for orthophoto classification because the orthophoto tends to lose their resolutions and texture information as we generate them. So for future work, we will combine the 3D point cloud models with our 2D images to further train our classifiers. Thank you for listening.
So, okay, thank you, YeSeul, for your very nice presentation. Maybe we have some time for a couple of questions before we have the coffee break. Maybe first I can maybe just ask something very quick. So is this the weather conditions or this, the environmental conditions have any effects on the, on the operation of your project?
Thank you for your questions. I would say that there is impact on any changes, including weather or environmental changes. But like I said, we were aiming to collect most of the data set, including those to cover those changes. So at the end, our model was able to classify the changes from the weather, but there was certain data set where there was huge differences where they build up very huge construction sites, and we were failing on those particular data set. But other than that, like normal changes like weather or seasonal changes, our model is able to adapt to those changes.
Okay, thank you. So I didn't see any question coming from the chat box, but maybe there is some questions from the auditorium, the host, please.
Yes, we have one question.
Okay, great.
Please.
Okay. Hi. First of all, thank you for your presentation, and I have two questions. So first one is I want to know about the train and test data set. And also second, I want to know, like you set the degree of, when you do the data acquisition, you set the degree. And I want to know why you set the degree like 45, 60, and I forgot, but yeah.
Okay, thank you again for the question. So for the data set, I'm not sure what exactly you were questioning, but to give you a brief information, we went to different test locations, meaning that there were different like environmental roads or other areas that we went, and so that was one of the variability. The other one was different seasons. We went to multiple times, so we used like almost like this entire data set except several data set for testing. Did that answer your question? And
so that means like you separate the there's some locations and you separate locations for train and test, right?
Plus, yes, there were different data set for different seasons. Like,
then how about the size of the data set? Can I ask about that too?
oh, yeah. So for each data collection, we collect maybe like 800 to 1,000. But like I said, we use the patch augmentation strategy. So based on the size of patch, there can be a differences, but we probably use like 5 data set for like our each models. So
okay, thank you. And second,
yeah, for the second question, actually our previous work also covers on this different flight parameters. So because we were creating these 3D point cloud models for labeling and other purposes, we were testing different combination of flying degrees or flying height to see like what best creates the 3D models. And plus it creates
Hello, yes, I'm Dr. Joe, so I will answer the question for you. Yeah, I'm advisor for YeSeul, so let me answer her question. So drone has a default is 90 degree. Vertically they collect the data. So our target is grass, is flat. It's not, there's no vertical, geometry at all. And then if you understand that the angle of the camera from the drones, 90 degrees is good for flat target. But when there's some vertical object you want to do it, you might need to change the angle, maybe less than 90 degree, maybe 45 degree, maybe capture better vertical surfaces. So we try to use different angles of the drones. So see which one is missing. Actually, we are actually collecting grass itself, 90 degrees is best because it's a flat surface. But there is some signs we want to use as a reference, like a rear guard or some traffic sign is vertical. So 90 degrees missing those vertical kind of surfaces. So we have to use kind of 45, 60 degree, whether we capture those vertical objects on the highway road. So we use different combination, or sometimes we mix two setup angle, 45 plus 90. So we mix those whole thing all together to model and then make a 3D actually model or 2D model. Yeah. Hopefully I answer your question.
All right. I think the time is up for this session. But I would like to thank very much again for all these presenters in this section for your very, very interesting and exciting projects and the presentations. So yeah, so I think now we have a time for a coffee break. Thank you. Bye-bye.
Thank you very much to our session chair and to all the participants. Now we can go to the coffee break and we'll be back at 3:30.